Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate. So this is the parent quadratic function. If we can master the parent quadratic function, then all the other function families we're going to study this year will actually become much simpler. It'll just be modifications of what we learned with this function. So what I have here is the coordinate plane, quadrants 1 and 2, and I have a table of values. So take a moment, get that ready. So what I'm going to do now is I'm going to use these particular inputs and I'm going to plug them in to my function here, right here, and then the outputs I get I'm going to sketch here. So when we have function notation, it's actually very advantageous, or in other words, a huge benefit to have things in function notation. So when I put 0 into f of x, it's going to look like this. This says f of 0. This means put 0 into the x spot, 0 squared, because my function says whatever you input, you're going to take it and you're going to square it. And so I get out 0 here. Let's see if that helps a little bit. All right, so this means this first ordered pair is 0, 0. My input is 0, my output is 0. Let's do the next one. So that point right here is 0, 0. Now let's put in 1. If I input 1, f of 1 means 1 goes into my function here. So it says 1 squared, 1 times 1 is 1. So this means if I put in the number 1, I get out the number 1. So 1. Now my scale here is by 2s. So 1 is about halfway right here. Okay. Now let's put in 2. So if I substitute 2 in, if I evaluate my function at 2, that means f of 2 means take 2 and substitute it in. So it's 2 squared, because my function says take your input and square it. 2 times 2 is 4. So this ordered pair is 2, 4. So 2, 4. Last but not least is positive 3. So this is f of 3. So this means take my function, evaluate it at 3. So it's 3 squared. 3 times 3 is 9. It is not 6. Oops, I was just about to write 6. So 3 times 3 is 9. So this means if I substitute 3 in, I get out 9. So 3 and 9 is halfway between 10 and 8. So we'll say right about there. So you can already start to see we're building the other half of our quadratic, which its shape is called a parabola. We'll come back to that in a moment. So let's do the negative side. So if I plug in -1, then that means I'm doing f of -1. Which means, according to my function, I'm going to take that and square it. That means I'm doing -1 times -1, which is a positive 1. So my ordered pair is -1, positive 1. So that's right here. -1, positive 1. -2 now. F of -2 means -2 squared. So that's -2 times -2 is positive 4. So this point is -2, 4. And the last one is f of -3. So now I'm going to take my function, I'm going to put -3 in squared. So that's -3 times -3 is positive 9. Now you may have noticed something, but the ordered pairs are almost identical, right? 0, 1, 4, 9, 1, 4, 9, but the signs are opposite. So here is the rest of our sketch. So it's not really supposed to be pointy at the bottom. It should be curved. Okay. And so this is the shape of a quadratic, and it's called a parabola. Okay, so it gets its own fancy name. Not every function has that. Actually, most functions don't even have it. Well, no, that's not true. Trig functions, you call them sine waves or sinusoidal, but that's another area that we'll get into eventually later. So here's our parabola. So let's go through some of our characteristics here. So we have the domain. Now the domain talks about the x values. So basically what you want to do with all these functions is assume the domain is all real numbers, meaning you can put any number you want in there. Positive, negative, fraction, decimal, doesn't matter, okay? 0, but if there's any restrictions, then our domain is going to be certain values. Now, right now, the first few parent functions we're going to deal with, we're not going to have any restrictions, okay? So the domain is all real numbers, which means we can pick -infinity, right? So it means we can go all the way to -infinity, which is a direction, it's not a number. It says you can pick any negative number that way, or you can go all the way to positive infinity on the other side. You could also write out the words all real numbers. The range, okay, so the range refers to the vertical element of it, so the outputs. So when we look at domain, we look at the inputs. When we look at range, we look at the outputs. So notice, is the range or the output's going to be all real numbers? In other words, will this parabola be through all the positives on the y-axis and all the negatives? Hopefully you can see that the answer to that question is no. This parabola is only existing on this side of the y-axis. So what that tells us is the range is not all real numbers. So where's the lowest it's going to go to? It's going to go to 0. Okay? And we can see that right here. The lowest output, f of x, is 0. Now, it actually is at 0. It goes through the origin, so we're going to put a bracket through it, because that means we can actually include that value in our range. Now, if we notice, though, it's going to continue to get higher up this way forever. So it's going in what's called a positive infinity direction. So the range is not all real numbers. It's essentially 0 to positive infinity. So it's all positive y values and 0. Another way you could write that is you could say that the y values are greater than or equal to 0. All right, let's keep moving on. Let's talk about the x-intercept. Now, because it's the x-intercept, that means the y-coordinate is 0 because it's touching the y-axis. So when you have a x-intercept, y is 0. So where does it actually touch the x-axis at? It touches it at the origin, which is 0, 0. Now, what is the y-intercept? Well, in this unique case, when your y-intercept is the origin, that means it's also, when the x-intercept is the origin, it means it's also your y-intercept. Because on a y-intercept, now x is 0. And notice when x is 0, y is 0. Next, let's talk about concavity. So concavity is when a function, or the quadratic, is opening up or opening down. Now, the parent quadratic function is opening up. So we say it is concave up. And that is because its beginning part, its a value, is positive, or it is greater than 0. If I'm greater than 0, I'm a positive number. If I'm less than 0, I am a negative number. Last but not least, before we get into something different here, is the axis of symmetry. Now, the axis of symmetry, actually, let me write it out. The axis of symmetry, abbreviated as AOS. That is the line that this is actually going to be symmetric to. Because if you notice, if I cover up half of this, do you see how it's reflected on the other side? Okay? So that vertical line is the axis of symmetry. Now, the vertical line is the y-axis, but it has an equation, and it is x equals 0. Last but not least, let's look at the increasing, decreasing, and the vertex here. The quadratic is unique in the sense that it has something called a vertex. Not all functions have a vertex, but quadratics do. The vertex is the highest or lowest point, or in other words, the maximum or minimum of your quadratic. In this case, because it's opening upwards, I have a minimum value, and it is that point at the origin 0, 0. Now let's talk about increasing and decreasing. This is something I noticed is that we struggled with on our practice problems today. So increasing is when the y value, so as x is going from negative infinity to positive infinity, when is the y values getting larger? So as I start at negative infinity, and this is where my graph is at. So as my x value increases, what are my y values doing? They're getting smaller. They're heading towards 0. That means they're decreasing right there. So the quadratic is decreasing at that time. So when does that happen? Well, where did I start at? Negative infinity. And let me do a better job there. Negative infinity. And when does it go until? It goes until 0. Now, I'm not going to actually include 0 because at the moment of 0, it's really not doing either value. It's not increasing nor decreasing. It's just at its lowest point. Now, let's recap. So at negative infinity, as I am moving along this axis here, I can see my function is decreasing. And then at 0, it's not doing anything. Now, I'm going to keep going though. So as my x value is increasing, now look at my function, look at my graph. See how the y values are getting bigger now. That is when it is increasing. And so when does it begin at? 0. And how long does it keep going for? Positive infinity. So when you describe increasing and decreasing, you're talking about when it is happening. That means you're going to look at the x-axis. Okay? If you're asking what something is, then you're looking at the y-axis. Okay, for example, what is the minimum? The minimum value, what is the x-axis? What is the minimum? In other words, what's the lowest value this function can be? 0. Does this have a maximum? The answer is there is none because it continues to increase on the sides there.